reason for processing the irradiated fuels is to separate the recoverable fissile material, the uranium and the plutonium, and to eliminate the fission products. Eurochemic has developed a version of the aqueous chemical process capable of dealing with the whole range of nuclear fuels used at present in all the European reactors built or being built. After the cladding which surrounds the fuel element has been chemically dissolved, the uranium rod is then dissolved in boiling nitric acid. The concentrations of acid and uranium in the solution obtained are adjusted before it is passed to 2 extraction cycles, which will separate first the fission products, then the plutonium from the uranium. These separations are brought about by putting the aqueous solution into contact with an organic solvent, tributyl phosphate, shortened to TBP, which diluted with kerosene. The 2 immiscible phases, formed by an organic phase and an aqueous phase, pass in opposite directions through the columns, whose pulsation ensures that the aqueous and organic solutions come into close contact. The uranium and plutonium nitrates in the solution form complex compounds with TBP, and these compounds are to be found in the organic phase. On the other hand, the major part of the fission products remains in the aqueous phase and is discharged from the column to be first concentrated, then stored. The organic solution, loaded with uranium and plutonium, is put into contact with an aqueous solution containing a reducing agent, which makes the plutonium pass back into the aqueous phase. In its turn, the uranium nitrate, which stays in the organic phase as a complex compound, is made to pass into the aqueous phase by means of a treatment with acidified water. This is the end of the first extraction cycle. The second extraction cycle for the uranium is simpler than the first. The uranium passes from the aqueous phase to the organic phase, and back again from the organic phase to the aqueous phase. The last persistent traces of fission products are gradually eliminated so that a satisfactory purity of uranium is obtained. After this second cycle, the uranium once more in aqueous solution is concentrated and sent through a column filled with silica gel, which retains the final impurities. The second extraction cycle for the plutonium is similar to the one for uranium, but uses mixer settlers instead of pulsed columns. Finally, the plutonium is precipitated with oxalic acid. The resulting oxalate is converted to oxide by calcination. This is the chemical flow sheet of the process adopted by Eurochemic, which carries out its initial work in laboratories rented from the Belgian Nuclear Research Center at Mol. Chemists recruited from the company's member countries study the different problems involved in processing a large variety of nuclear fuels in order to develop a process suitable for industrial scale application. Research is carried out in the 3 principal fields of the process: dissolution, extraction, and purification of uranium and plutonium. The dissolution equipment must be able to deal in turn with the decladding, the dissolution of the fuel element core, and the recovery of the nitrous vapors formed during the chemical reaction. Pulsed columns, 5 for the first cycle, 2 for the second, are used for the extraction process, which is performed by forcing the aqueous and organic solutions through a series of perforated plates installed inside the columns. The final purification of natural or slightly enriched uranium is carried out in a silica gel column, whereas plutonium and highly enriched uranium are purified in mixer settlers. In these mixer settlers, the process is similar to that in the pulsed columns. The progress of the extraction can be seen from stage to stage. The plutonium, or the enriched uranium, passes from the aqueous phase to the organic phase, or from the organic phase to the aqueous phase. At the end of the process, the remaining fission products have been separated from the plutonium or the enriched uranium. To gather the plutonium, a continuous precipitation system has been developed in the Eurochemic laboratories. Another technique for recovering plutonium by fixing it on ion exchange resins has also been studied. The development of these processes has required the building of a testing station. Studies have been made with a glass dissolver of 1/3 the size, with pulsed columns of the actual size, and using natural uranium. The technicians have developed equipment adapted to the special needs of the Eurochemic plant, using air pulsation to avoid mechanical equipment which requires regular maintenance, air bubbling for controlling the position of the interphase inside the columns, air lifts to transfer liquids with the help of air bubbles. All these systems have been designed above all to reduce to a minimum the need for personnel to enter the active zones. In the pilot hall of the research laboratory, there are dissolvers, extraction columns, and mixer settlers identical with those of the plant. The dissolver must have the form of a ring, the shape necessary to avoid all possibility of a criticality accident. Jackets carry steam and hot water necessary to reach the temperatures required by certain dissolutions. The equipment for recovering the nitrous vapors has reached full scale. A glass column has been installed alongside the other steel columns so that visual control can be used. The chemists of the laboratory can hardly be distinguished from those who will operate the plant. The same activity goes on around the various pieces of equipment, the same close watch on the numerous control panels. Even though the whole of the plant is not yet in operation, there is intense activity everywhere. Equipment has been installed, the dissolvers are carefully moved and assembled in a tight cell. Huge tanks will store effluents of medium activity. Other tanks, ring-shaped to be safe from criticality, will be used to store solutions containing large amounts of fissile material. The pulsed columns, brought by rail and road to the plant, finish their journey by air. Made in one piece, completely welded, containing hundreds of perforated plates like those to be seen in the glass columns, there was no question of dismantling them and putting them together again inside the plant. columns are lowered one by one into their cells, through holes left for this purpose in the roof of the building. After the 7 columns have been installed and connected to the maze of pipework, it is possible to check their operation and tests begin. In the reception and storage building, the stage of erection and testing is long past. Operation has begun, and irradiated fuels brought in from the member countries are being stored before treatment. When it arrives, the transport container is taken to a room where it is washed to remove the dust collected during the journey, and where the level of radioactivity inside it is measured to find out if any of the fuel element claddings are leaking. The container is submerged in the reception pond and the elements are unloaded underwater. At a depth of 8 meters, the fuel elements are placed one by one into the storage baskets. A moving platform enables the baskets to be transferred through a lock to the storage pond. The number of elements already being stored increases every month, assuring a considerable operating program for the plant, and confirms the hopes of the 13 OECD member countries who founded Eurochemic.